Hi there, welcome to your lesson on integration by substitution. Considered kind of a tricky topic, but I'm sure you're going to figure it all out here. Let's get started. First of all, let's remind ourselves that when you take a derivative of something and get a result, then you take the integral of that result, you get back to the original. Derivatives and integrals are reverse processes. They undo each other. And of course, Batman is the best. Okay, let's jump into our lesson. So, flashback, a little bit of a recap on integrals before we get started. First of all, our rules of integrals. The first rule we know is the basic power rule. It is the rule that tells us when you have something to some power, you add 1 to that power and you multiply by 1 over that new power to get your integral. All right, then we reminded ourselves 1 over x, integral of that is ln x, and integral of ex is e to the x. Okay. And last lesson, we also looked at sine and cosine. So the integral of sine x is negative cosine x, and the integral of cosine x is sine x. We also looked at integration with linear composites, and we looked at the idea of having a linear function composed with another function, so a linear function within another one. So here we have a power function with a linear one inside, and the rule there was we take our linear part, and to account for that, in our integral, we multiply by 1 over the coefficient in front of the x. And otherwise, we just apply the power rule. Add 1 here, multiply by 1 over that new power. But that 1 over a accounts for the linear portion. Okay, and we apply that to sine and cosine, and we notice the same thing happening as well. Here I have a sine, integral of sine, with a linear function composed inside of it. Therefore, when we have the integral, we do 1 over a, 1 over that coefficient. Otherwise, it's just an integral of sine, which is negative cosine. Likewise, with cosine, we do the same thing. We have cosine with a linear function composed within it. Therefore, we multiply by 1 over a to undo that part, and that's our integral. Great, with all that on your mind, you're ready to jump and take the next step. Let's get going. So let's begin with this. We're going to take a derivative of this. Okay, so we have this function here. I can see a power function, but within there's a linear function, and there's some multipliers in front. You might be wondering why those are not multiplied and simplified into 1 over 10, but we'll see. This has an illustration of what we're doing. I needed to start like this. So the derivative of that is, okay, let's check. You will apply the chain rule, so you'll take the derivative of this, so drop the 5, which is right here, lower the exponent to 4, which is right here, and then since we have a linear function within that power function, we also have to multiply by the derivative of that linear function, which is just 2, and we can see the 2 is here. So basically there's that 5, there's that 2, everything else is the same other than this reduced exponent. Simplify this. Well, this 2 will cancel with the half, they'll be gone. This 5 will cancel with the 1/5, those will be gone. So you're left with just this. Okay, so that tells us if we went in reverse order, if we took the integral of this, what we just came up with, the integral of that would take us backwards through the process and back to the original. So that means the integral of that is this, what we began with here, plus c. Okay, so derivatives and integrals are reverse processes, right? Okay, so how about this one here? Let's take an integral of this one. So we just noticed here, to take this integral, all we did is raise this power, right? There it is, 5. And then multiply by 1/5, and then multiply by half because of this 2 here. So can we apply that same linear kind of rule here? Let's take a look. By the same kind of rule here, to take this integral, we can raise this power, make it 5. Okay, so there's the 5. We can multiply by 1/5 because now we have a power of 5, so we multiply by 1/5. And then we look inside and we say, what's the derivative of that? Oh, derivative of all this is 2x. So I'm going to multiply by 1 over 2x. Just like here, we said, what's the derivative of that? It's 2. Oh, I'm going to multiply by 1 over 2. So I'm doing the same thing here, except for now, instead of a 2, I have a 2x because the derivative of this is 2x. Will this work? Is that really the integral of that? Will this same rule that we applied here work here? Let's check. Let's go backwards. Let's take the derivative of this and see what happens. Because if we take the derivative and we get back to here, then that rule works. Okay, let's check. Derivative of this, well, first of all, I can simplify it some more. We have 1/5. I brought this 2x up like that to -1. And now we have 1/5, but then we have a function times a function. So here we will need to apply the product rule or the quotient rule if you left it like this. And product and quotient rule, if you remember, they're going to get us something much more complex. There's going to be adding, subtracting, there's going to be fractions in there. And guess what? You can try it if you want, but guess what? It's just going to make it very complex. It will certainly not take you back here. And what that tells us is that applying this rule here that we had with the 2 here becoming a 1 over 2 here, it doesn't work when this function, because in this function, this part was linear. And that's why we say this rule works for when there's a linear composition. But this thing here, right here, is not linear. So that works because it's linear, but here it's not linear, non-linear. So that rule here, we cannot do 1 over the derivative of that. It won't work. So that's why it does not work. Don't memorize this as something that works. It does not work. It only works when this is linear. So now the question is, how do we deal with things like this? When this is non-linear, how do we take the integral? All right, and that's what this lesson is all about. Let's take a closer look at something else here. So we have this function here. I'm going to take the derivative of that, and the derivative is this. I drop the 5 in front, there it is. Lower the exponent by 1. Okay, and then that's that. And then we have this nonlinear function there, but by chain rule, we have to multiply by the derivative of the inside function, which is 6x plus 5. So we did the power rule here, and then we multiplied by the derivative of the inside. Okay, so that can simplify to this because those cancel, the 5 and the 1/5. All right, there's our derivative. That means our integral of all this will be the original function. And now let's take a look at something we see here. Do you notice something interesting when you look at this and this? Do you notice something interesting there? Okay, I hope you notice that this here is a derivative of this. So when we have a function where we have two things or different parts to it, and one of the parts is a derivative of the other part, then we can apply integration like this, where basically we say, okay, this is the derivative of that. Therefore, I'm going to deal with the integral of this. So look at this. Integral of this is raise it by 1, that 4 becomes a 5. Put a 1/5 in front because we do 1 over that power. And then that's it. That's it. If this is the derivative of that inside part, that is canceled out. Because when we take the derivative of that, we multiply by the derivative of that, and that's where that comes from. So that part kind of disappears. So that's a nice little shortcut. As long as you can spot a derivative of another part, it works. So let's take a look at what this rule, kind of how it breaks down. It basically looks like this. If we have an integral and there's a function and another function inside of it, and then we also see in the integral we're multiplying by the derivative of that inner function or that other function, then we can use this shortcut here. So here that's what we saw. We saw a function, another one inside of it, and over here the derivative of that inside function. See, derivative of g of x. All right, so we're looking for that kind of pattern, and we're going to see if we can figure it out in some other problems. This is called, by the way, a process called integration by substitution. We didn't make any substitution in what we just did, but you're going to see how we're going to use it here. So we're going to take a look at the same problem we just had and show you what integration by substitution means and how it's applied. So here's the one we just saw. And that one we noticed again that this is the derivative of that. Therefore, we just take the integral of this and we get to this. So now by substitution, here's how it works. You look at the thing that you know you're going to take the derivative of. So 6x plus 5 was the derivative of this. You can see it just by looking at them. So this, you set that equal to all u. Usually we use the letter u. So we say u equals that. Then you take the derivative of that. Okay, so you take the derivative of this, du dx, and it's 6x plus 5. And now you can confirm, okay, yes, I saw it correctly, that is the derivative. Now you make a substitution. So back into your original integral, you substitute your u and the du. So check it out. So this, all of this is replaced by u. So it becomes u to the fourth, u to the fourth. And then we multiply that by this. This is replaced by du dx. So we just put du dx instead of the 6x plus 5. And now here's something interesting that happens. We see du dx here. These two dx's can cancel and they become like this. So we just have u to the fourth power of du. So it means we're taking the integral of this in terms of the variable u. We've changed the variable to u, so now we're doing in terms of the variable u instead of the variable x. Now, I don't want you to think that this is a fraction. This is not a fraction. We're not canceling these because it's a fraction. Don't get that rule in your head. I'll show you on the next slide what's happening here, but basically, we do leave it as du here. So now you take the integral of u to the fourth, And we know that it's raise the power by 1 multiplied by 1/5 plus c. Now we substitute back in what u was, and u was just 3x squared plus 5x. So we put that back in there, and guess what? We come back to here. So a lot of students, once they get used to this method, they prefer to just spot the derivative like I did here and jump right to the integral. But some questions get a little trickier. You'll see those soon. And in those cases, you should make the substitution and see what happens. So this is called integration by substitution. Pause and take a look at everything here closely. Okay, hint. This is called u substitution. I just said that because we often use the variable u to do this. Okay, why did the du over dx times dx become du? Again, I told you it was not fractions. These did not cancel. So now this slide is optional for you. You can pause and study this, but this is a proof or kind of a reason for why that happens. This is much beyond our course, but maybe you're interested. So pause now and take a look and see if you can make sense of that. All right, but let's try some more problems. So look at this one. Remember, with this method here, we're looking for something that is maybe the derivative of something else. So do you see that here? I definitely see it. That 6x plus 7 is definitely the derivative of all this here. So what will the integral of this be? Okay, you can check your work here. So it's always going to show you with the substitution made. But maybe you spotted this one like I said in the beginning. Oh, I see this as a derivative of that. Therefore, I'll take the integral of this only. And you can see that happening here. The integral of just this is this. See the 6 there and the 1/6? Done. Because that cancels away because it is the derivative of that. But here's the u substitution. You should take a close look because again, you'll need this substitution when the questions get tougher. Okay, let's take a look at another one. And by the way, when you just look at it and don't do the substitution, we call that integration. Oh, let's go back. By inspection, you see it, you see the derivative, and then you just go for the integral. If you want to use u substitution, sometimes it's more helpful for sure. So let's take a look here. So again, look for the function. It takes on this form that we talked about, where the derivative of the inside part. Take a look here. Do you see one part of it as being the derivative of another part? Yeah, definitely. Look, check it out. This 2x minus 3 is the derivative of this inner part right here. So now you know that this part is the part that disappears. You can, I'm going to show you the substitution here again. So I'm going to let u equal the part I'm going to take the derivative of. So that thing right here. Then take the derivative of that. You get that, and it confirms that there's the derivative right there. Now we'll make the substitution back into the original. So now we have u to the 1/3 because all this became u, and cube root of 3, cube root is 1/3 power, right? 1/3 power. And then this was replaced by du dx. These are gone. We have a du. Take the integral of u to 1/3. That means you add 1. So that means you're adding 3 over 3 becomes 4/3. And then the flipped over fraction right here because it's 1 over 4/3, which becomes 3/4. And then this final step, put the u value back in. Again, this one is an easy one by inspection. We saw this as a derivative of that. Therefore, we could have just done the integral of this and arrived at this answer here. All right, let's try another. Check out this one. Do you see something that is a derivative of something else? Definitely. This part is the derivative of the bottom part. Let's try it. What's the derivative of the bottom? Drop the 4, 12x cubed minus, yep, see? This is the derivative of that. Therefore, what's the integral? Okay, let's check our work. I'm going to show all the steps. Check it out. Here's our u, the thing we're going to take the derivative of. Here's du dx. We take the derivative of it. Put it back in here. All right. Notice we have 1 over u here because the u is on the bottom. 1 over u. This cancel, and you get to ln because remember the derivative of 1 over u is ln u. And we put the u back in like that. Great. Hope you're getting the hang of it. Pause and take some notes if you need to really consider it carefully here. Let's look at another one. Try this one. And now check your work on this one. Definitely you see this is the derivative of that. You could have followed those steps and got into this ln value right here. Pause again, check your work carefully. How about this one? A little bit tougher. And actually, let's pause here. I can see I'm running out of time for this video. This is going to be continued in a short follow-up video, and it's going to take you through this question and a little bit more with sine and cosine, but not much. All right, see you soon. Okay, so we're looking at this problem, and in this one, Again, the inspection method might be easiest, right? We look at our integral, we see something, and we see another part, and clearly one of the two parts is a derivative of the other. Like we can see this is a derivative of that very clearly. So when that happens, we've inspected it and we've seen that derivative. Therefore, we can ignore that derivative and just go ahead and do the integral of the rest of it and get to our answer. Okay, but there's times where inspection is not enough and using the whole substitution method is necessary to really clarify things. Let's take a look at that in this next example. So in this one, we're going to begin with this situation, okay? So now we have an e to some power function and then we have 8x here. So one part is 8x, one part is this. And you're inspecting it and thinking, okay, what is one of these two parts the derivative of the other? Well, clearly if you take the derivative of 8x, it's 8. So this certainly is not the derivative of that. Okay, let's look at it backwards. What about this? What's the derivative of all of this? Well, the derivative of e to this power is e to that power times 8x. So now you're saying, okay, maybe all of this is u, because if all of that is u, I end up with some 8x and then more, but you end up with 8x and too much. So that's too much. So let me show you this one. You can go even further. You can say, rather than looking at this whole e to this power, you can look at just the exponent itself. So what's the derivative of the exponent? Okay, the derivative of 4x squared plus 1 is 8x. So we found it. We found the thing we're going to take the derivative of. So we'll set u this time. We notice that this is the derivative of this. So we set u equal to this thing. Then we take the derivative of that to get our other part, right? Derivative of that is 8x. So du dx is 8x. Okay, great. So we have all our pieces now. So we can replace them in here. So this 8x is replaced by du dx. And this is replaced by e to the u, because this is u. So here's what we have. E to the u, du dx dx. The dx's are gone and we're left with just e to the u du. Okay, that's an easy integral because the integral of e to the u is just itself. So our answer is e to the u. But now we replace the u back with what we had here and we get this. So again, this would have been fine. Of course, substitution is great, but it would have been fine to do this one just by inspection, because as soon as you spot that something is the derivative of some other part, you can jump and ignore that and then just worry about that derivative. So that could have been done there. But let's look at when this changes, and substitution is really, really helpful in these cases. Look, this is almost exactly what we had here, but instead of 8x, we just have x now. So clearly the derivative of the exponent will not give you this piece. So it won't be as simple as we had here, but we're going to approach it the same way. So check it out. We're still going to set u equal to that because we know the derivative of that is close to what we have here. It has an x in it. It also has an 8, but it has the x. That's the main thing, that it has that other functional bit, and the coefficients are easy to deal with. Watch what we're going to do now. We're going to have to make a substitution here. And we're going to substitute this and this. If we're going to replace x, well, we need to solve this for x. So what is this when you solve for x? What do you do with the 8? Well, the 8 goes on that side with the du dx. It becomes a 1/8 there. It's like dividing by 8, so there it is. So now that, all of this will be substituted in for x. So here's our substitution in this case. We have the 1/8. It's there. They put it outside the integral because it will go out. But anyway, there's the 1/8. There's the du dx, and here's the e to the u power, like we have here, the u power. So now we can take the integral of that. Again, you could have begun with the 1/8 in there, but when we have an integral, we can take that 1/8 out right away. So integral of that, well, first of all, the dx's are gone. It's just du. And now we have 1/8 e to the u is our integral of that, because the integral of that is u, and then replace the u and you have that. So notice how these are similar, but also how they're different, and how we have to take this extra step here. I would suggest pausing here and just taking a look again about the similarities and differences here to really understand how substitution can be applied. Okay, so with that in mind, now you should be able to do this one. So try a similar approach to this one, and again we have e to some power here. See if you can figure this one out. Okay, let's check our work. In this case, we set u equal to that exponent, because the derivative of that, you can see here, is 6x. And 6x is close to what we see here. We see 2x. Okay, well, we have 6x, but we see 2x. So we need to turn this into 2x right here so we can make the substitution. So to do that, you can divide this by 3. and then you'll have 2x. So that means divide this by 3 also, which means multiply by 1/3 like this. So this turns into this. And now we have something here that's identical here. So you make the substitution. And so let's see. And notice, did we have one like this yet? Let me go back 1 second. Yeah, I just went back and checked. There was one that was similar to this before, because there's kind of two different approaches going on here. You may have noticed one like this with the greens and reds earlier, where it did a slightly different approach. It, rather than keeping the dx here, it moved the dx to that side. So imagine this dx was under here, which is the typical approach. This is a little different. So dx was under here, then you'd put in du dx here and then it would cancel. But anyway, the point is you end up with the same step right here. So if you kept the dx under there and substitute in, you'd end up in this step anyway. So now we have this. You take the integral of e to the u and you get 1/3 e to the u. Substitute back in your u value and you're there. Okay, again, pause if you need to see exactly how this substitution bit worked here. All right, I think we're ready to go back to sine and cosine now as well. So let's remind ourselves, the integrals of sine is negative cosine and the integral of cosine is positive sine. Okay, and we also looked at the linear rule with sine and cosine, which we'll come back to here a little bit. So the linear rule, let me go back, tells us when you have a linear bit here, you end up with that 1/a here and 1/a here. Okay, so let's do a couple simple ones like this first, and then we'll try some substitution ones. So here's a very basic one, and here's a basic one with the linear piece. See if you can do these two. Okay, first one, the integral of, okay, that's linear, I mentioned that. The first, here's the answers. So in this first one, here's our integral. Okay, 3 came out. Integral of sine x is negative cos, we get that. Second one, integral of cosine is sine, but since we have this linear bit, we have to multiply by 1/4 in front of that. Great, basic ones, just to get your sine and cosine integrals back. And now let's look at two tougher ones. So what happens when the composed function is not linear? So again, we have those sine, we have the sine with the linear bit, but what happens when the function that goes in here is not linear? Let's take a look. So here is one like this. Here we have cosine with this function composed into it, but this is not linear, so now you're going to have to use the substitution method. So try that with this one. Can you substitute in and find an answer for that integral? Okay, let's check our work. There's that bit. If you take the integral, sorry, the derivative of that, you notice you will get 5x to the fourth. So that tells you you have x to the fourth, right? So that can be your u, okay, but it's nonlinear. So let u equal this part, and then du dx is 5x to the fourth. Notice we have the x to the fourth and x to the fourth, so we can almost substitute it, but not quite. We have to get rid of this 5, so we're going to divide by 5, so 1/5 goes here on the side with du dx. Alright, substitute in, we get this. So cosine of u, because we made this u, the 1/5, because we have that 1/5 here, and then the du here. So now you have an integral of cosine, which is just sine. We have the 1/5 in front, and now you substitute u back in. Okay, so again, notice they used a technique here where they took the dx and you moved it to this side. The dx could have been under the du here, and then it would have led you to the same place. Okay, let's try one last one like this. So we have another one with sine here, another one with cosine. Both of these will require the u substitution. Let's see if you can do it. Try C first. Okay, in C, here is our work, and D is given to you as well. So here, I made a substitution for e to the x, because the derivative of that is e to the x, and I see it right here. So now I can, by that substitution, I can rewrite it like this. Sine of u, and then there's the du dx. Those dx's are gone. We're left with sine u du. The integral of sine is negative cosine. Put the u back in, we're back to here. Alright, D, a little more complex. But if you take the derivative of this inner part, maybe you noticed it's 12x cubed, so we have the x cubed. Alright, great. So u is 3x to the fourth. Du dx, 12x cubed, the derivative of that. Dx cubed matches that, but to make the substitution, we don't need the 12 here, so I'm going to divide by 12 over here. And now I have that. Okay, that can be substituted in, it's done right here. 1/12 du dx, and then times cosine of u. Du dx, and dx becomes du. The 1/12 can be moved outside. Take the integral of cosine, it's sine, and there, put the u back in. Great problems, lots of different skills there. Derivatives, integrals, sine, cosine, linear rule, everything together. Hope you did okay with that. We will see you soon. Great job.